If you have any trouble in the problems that we have, okay, I'm going to read it. And we learn about conditional probability. And I gave you an example of selecting two cards, one after one, in which we felt like if you select two cards, one after another, and you replace the first card, and the probability that the first one is S, I'm sorry, that the second one is S, given that the first one was S, will remain the same. That is an idea for independent events. For example, if I roll a die twice, what I get on the first roll is independent of what I get on the second roll. And what I get on the second roll is independent of what you get on the first roll. So in some instances, independence comes from the experience that you have conducted. But we want to give a formula that will help us to determine if two events are independent or not. Two events are independent, actually, if they do not affect each other. For example, if we say that two people are independent of each other, it means that what one does not affect what the other one will be doing. If we say that two individuals are mutually exclusive, that would mean that they cannot do anything together. That is the meaning of mutually exclusive. If one sees the other one going to eat, he will not go there to eat. If one knows that another one is going for a party, the other one is not going to be there. So they are mutually exclusive. Independence means that they do things independent from each other. For example, the fact that one is doing one thing cannot tell you whether the other one is going to do it or not. So, in terms of probability, we write it like this. Most generally, people write that two events are independent. The probability of A intersection B is equal to the probability of A and probability of B. We can show that these three statements are equivalent. We can show that 1 is equivalent to 2, equivalent to 3. To do this, I will just write that. Suppose 1 is true. Suppose probability of A given B is equal to probability of A. And now, probability of B given A is equal to probability of A intersection B divided by probability of A. Now, by the product rule, probability of A intersection B is probability of A times probability of B given A. Or we can also write it as probability of B and probability of A given B divided by probability. So I put this one here, but it's not very important. This is what will be important. So probability of B given A, if we know the probability of A given B equals to probability of A, we want to show the probability of B given A is also equal to probability of B. So we can say that because we say this is true from 1, so this equals to probability of B. I'm trying to show is that any of this definition is correct and equivalent to the other one. If we assume that one is true, from one we can get 2. And from 2, we can mark that this shows that 1 implies 2. Now we want to show that 2 implies 3. Probability of A intersection B is equal to probability of A and probability of B given A. And from 2, probability of B given A is probability of B. So that shows the probability of A intersection B. And now we can show that 3 implies 1. We know that probability of A given B is equal to probability of A intersection B divided by probability of B. And this is equal to probability of A and probability of B. So what I have shown here is that 1 implies 2, 2 implies 3, and 3 implies 1. So when I show this circle, it means that they are equivalent. Two events that are not independent are called dependent. Let's look at this example. Suppose that the chance that the student earns a grade of A in a mathematics course is 40%, and the chance that the student is assigned an A in engineering is 70%. If these events are independent, find the following. The probability that the student receives an A in both math and engineering. Let's say that A is A in math and B is A in engineering. The first question here is, what is the probability of A and B if the two events are independent? If the two events are independent, what will be the probability of A intersection B? Remember the formula we just have? What is probability of A intersection B if A and B are independent? Probability of A times which is 0.4 times is equal to these two events. Observe that probability of A is 0.4, probability of B is 0.7. If I ask you the question, even two events with this condition, can we say they are mutually exclusive? Can we assume that the two events are mutually exclusive? Do you remember what mutually exclusive is? If A and B are mutually exclusive, what will be the probability of A union B? Probability of A, then multiply or add, plus probability of B. This is the condition for mutually exclusive. If probability of A is 0.4
and probability of B is 0.7. If A and B are mutually exclusive, what will be probability of A union B? What is probability of A union B? Pardon? 1.1. Does that make sense? So, impossible. That is a contradiction. Right, Jacob? When we get to a contradiction, that means that the premise is false. So A and B are not mutually exclusive. I want you to see that there is no connection between mutually exclusive and independent. I use this example because they are independent, and from the information we have, they cannot be mutually exclusive. So now B. Find the probability that the student receive an A in either in neither course. What do we want here? What is the event in B? How will we express the event B? Pardon? Complement of what? Complement of A union B. If we had said either, it will be or. Neither is the opposite of or. So we are looking for the probability of A union B complement. Which is equal to 1 minus probability of A union B. Now, I could also ask you the question, if probability of A equal to 0.4 and probability of B equal to 0.7, what is the probability of A union B if A and B are independent? You might see some homework problem like that. If A and B are independent, probability of A union B, always just write the definition that you know. Is probability of A plus probability of B, and what? In general. The addition rule in general. The number of elements in A or B is the number of elements in A plus the number of elements in B, and what do we do? Anthony? Minus probability of A intersection B. Does it make sense? We want to, the way to remember these things is to write it often and often. So we had that one for mutually exclusive because this is 0 for mutually exclusive. If A and B are mutually exclusive, this will be 0, right? Mutually exclusive means A and B is impossible. So that is why we have just this part. Now, this is the definition of the probability of the union. It is probability of A plus probability of B. If we have already had the answer for A part, we are going to write this 0.4 plus 0.7 minus what? Pardon? 0.28. 1.1 minus. Use your calculator. Pardon? So the third question is C, which is the probability that the student receives
exactly 1A. Exactly 1A. Think about it this way. This is so we want this one. And this one. Here is so the events for quotient C is probability of A minus union A minus A. That is exactly what A will mean. Either the student has A in maths and not in engineering, or in engineering and not in maths. Does that make sense? Exactly one is that you have one in A in maths and not A in engineering. But that's the meaning of the difference that we define. So are these two sets mutually exclusive? Can an object be here and here? If it is here, then it is not in B. If it is here, it is in B. So it cannot be here. And vice versa. So the two are mutually exclusive. This will be A plus B plus probability of. Now we are going to write that probability of A minus B is equal to what? Probability of A minus B. Observe this. Look at this diagram. This is A minus B and this is A intersection B. So the probability of A is probability of A minus B plus probability of A intersection B. In general, so we are looking for this probability of A minus B, the probability of A, probability of A. Do we know probability of A intersection B? What is probability of A? What is probability of A intersection B? This will be. We will do the same for probability of B minus A, which is equal to probability of, not the probability of B minus probability of A, because if you are doing that here, you will get a negative number. Operation of probability is not a linear operation. Okay? This is not really like a mathematical subtraction, arithmetic subtraction. This is just a sign. So we are going to do the same here. Is probability of B minus probability of A intersection B. I think that I don't know looking at the name here, which is 0.7 minus 0.2. Which is what? So the probability of A minus B minus B minus
events. There is a question that you will see on homework, which I am going to start here, and you will complete it at home. Suppose you have two events, A and B. We have A and B. This is probability of B, probability of B complement. This is probability of A, probability of A complement. Suppose probability of A is equal to P, and probability of B is equal to Q. What should we write here? Yes. Should we write P plus Q here? What should we write here? Where do you get the P to write here? Usually the total of what? Listen. Right? We should write here 1. We don't know those probabilities, but it will boil down to 1. Probability of event plus probability of its complement should be 1. What should we write here? Here is the intersection. Here is probability of A intersection B. Probability of B intersection A complement. Probability of A intersection B complement. Probability of A complement intersection B complement. So I will ask you the question: if A and B are independent, show that A complement and B complement are independent. A complement and B are independent. A and B complement are independent. And you will want to show that you want to complete this. We are going to do it all together before you do it again at homework. I will still leave it as a homework problem because I want you to manipulate proofs, how to prove. So what will be probability of A intersection B if A and B are independent? Daisha, what is probability of A intersection B when A and B are independent? Pardon? Yes, what should it be? In terms of probability of A and probability of B. Okay, probability of A is P, probability of B is Q. What is probability of A intersection B? Look here. PQ, right? So this is how what we are doing. You should pay attention to what we have said. In order to answer this question, most of the time is from what we have done that I ask you those questions. So we are going to have here, I'm going to remove this. P times Q. So, we don't know what to say for these ones. What can we say here? Now, I'm going to remove these numbers. If you like, you put Q. So what should be here? We are practicing how to complete this table. What should I write here? Here we will write this plus this equals to that. Do we know that? This plus this equals to that. In any table that we have, when we have this contingency table, sum of the rows equals to total of the rows. So you have this plus this equals to that. So what should be here? Maybe, what do you think we should write here in terms of PQ and Q? If this plus this, let's say this is A. If this plus A equals to Q, what should be A? Aisha, any idea? Why do you say no? If I say PQ plus A is equal to Q, what is A? Solve for A. Don't make it more difficult. What is A? Jacob? Q minus PQ. You answered a question that's more difficult than this on your homework. Solving quadratic equations, right? This is a simple equation. Do we get that? So we want to use simple things to develop a little bit more complicated ones. So we are going to write here Q minus PQ. So what should we write here? P minus PQ. Now what will we write here? You will complete this one. Now I'm going to choose, I will do this one. When I am here, it is probability of A intersection B complement, which is what we are actually calling A minus B. This is probability of A intersection B complement. I want to show that it is equal to probability of A times probability of B complement. But from our contingency table, it is equal to P minus PQ, which is P times 1 minus Q. And P is probability of A. 1 minus Q is probability of B complement. I've proved that if A and B are independent, then probability of A intersection B complement equals to probability of A times probability of B complement, meaning that A and B complement will be independent. To do this, I made use of my contingency table. what I'm doing here
is just a general interpretation of what we did. We say probability of A minus B is equal to 1, 2. So we could say that probability of A minus B is probability of A intersection B, which is probability of A. Probability of A is 4. Probability of B complement is 3. If you assume that, we are going now to know that it is true, but before we proceed in this course, until we go to 3 or 4, 3 or 5, we will understand that when two events are independent, their complements are also independent. They are independent with the complement of the other and all that. And that comes from this table. I've done this, you could do this, and then try to do the last one.
probability of A complement intersection probability of B.
I want us to do another application of the Bayes theorem on the credibility problem, just to complete this chapter. If somebody is bad, because he was bad last year, will he be bad again this year? If somebody lied to you one time, doesn't mean he will lie to you a second time. Those are the type of questions we are trying to address here. And now we are using an example that actually reflects that, but this is just part of what we call conditional. So soon some of you might want to buy a car and get insurance. So you will be interviewed by the insurance agent to determine your credibility. Are you a good or a bad driver? So we assume you are an average customer, so that there is an 80% chance that you are good, maybe a good driver, and 20% chance that you are bad, let's say bad driver. Then A be the event that you have an accident in the next year. For simplicity, we assume at most one accident. What we are trying to say, here is that saying that we will have an accident is like we will have at least one accident. Suppose we observe an accident in the first year. Find the probability that the individual is good. So we are going to make a table, understand how to solve this type of problem. That's what we do every day. If somebody looks somehow, we want to determine if that person is, based on what the person has said or has done, and we conclude that that person was like this or like that. You get what we are saying here. We want to know the precedent. From the effect, we want to determine the cause. So we are going to make a table like this. Good. So suppose we observe an accident in the first year.
What is the probability that you are good? Let me make sure that we have all the information. I'm feeling as if something is missing. Yeah, I typed this problem without including. There is something missing there. The probability that a good person will have an accident. So this problem, I pick it as a continuation. There is a long statement that I will just summarize it by telling you what it is. So using the Bayes standard, is missing here. Using the Bayes standard, the Bayes standard is that a good person has a 10% chance of getting into an accident, and a bad person has a 50% chance of getting into an accident. So Bayes standard, this one is given. Probability that you have accident given that you are good is 0.1. Probability that you have accident given that you are bad. So we write here accident. So based on what we have here, probability that you are a good person is 80%. The probability you are a bad person or a bad driver is 20%. So this is 0.1. This is 0.9. So suppose we observe an accident in the first year. What is the probability that you are a good driver? Look at what is here. Probability of A given you are good. Our question in A is what is the probability that you are good given that. I'm going to correct this one on your PowerPoint, but I want you, it is in your textbook. There is a long text that explains that first, the standard that is here. So I'm going to put that, correct that on PowerPoint. So look at what we have here. This will be equal to, using the Bayes theorem, this is probability of get an accident and you are a good driver, divided by the probability that you get into an accident. So this is equal to probability of A and G divided by The probability of A will be you have an accident in general. Having an accident in general, that's probability of A. You can have an accident because when you are a good driver, or an accident when you are not, when you are a bad driver. So people always ask the question, is it because he's told that he is a thief? That's the question people always ask. Is it because he lied that he's always a liar, that he's a liar? So that's what people always say. It just happened. And that's why we are calling this type of question credibility question. Is it because he had an accident that you will raise my insurance? So those are the type of questions people really have to ask. Because your insurance is charged depending on whether you are a good or a bad driver. So, what is the probability of A and G here? Probability of A and G will be probability of G and probability of A given G. Do we see that? This line will go to A and G. This line will go to let's say A and B. So probability of A and G will be with 8 times 40. Here, which one stand for probability of A given G. And here we are going to have 0.08, which is this one, plus 0.5 times 0.2. 0.5 times 0.2 is 0.1. If you multiply anything by 0.5, it means 0.5. So this is 0.08 divided by 0.1. You can complete this exercise and please do the homework. We are done with chapter 2. We want to start chapter 3 on Wednesday, but I will encourage you to do your problems. The exam will be on chapter 1 and 2, but we will move on to chapter 3. We will be doing, please do the homework so that on Wednesday we work problems. I don't want to just choose problems because I don't know which one you may really want to understand. So if you don't, I will continue with chapter 3, which is not the best,